Hello and welcome. My name is Elhelw. Today I'm going to talk about a topic that many people probably do not associate with databases, but it actually has a very tight relationship with databases. Today's topic is full text search. What is full text search? I'm sure lots of us have heard about it. Actually, most of us, if not all of us, use it on pretty much a daily basis. Full text search is the capability of finding information within a large volume of text-based documents or data using a search query. Usually this means that we have a big or large collection of text fields and we want to find words within those text fields using a partial matching or variations of the terms that we're looking for, so it doesn't have to match exactly the terms that we're looking for. And also it often involves ranking the results based on their relevance to the search query. What text search is not, it is not just simple keyword or tag matching. Like, it's not just a matter of having a bunch of keywords associated with the data and you want to look for certain tags or certain keywords. No, you're looking at the full body of text. It also is not comparing structured fields or exact values like we do usually in databases when we're looking at the whole value of a field and so on. So again, this is not what text search is. It has to do with looking at the entire text content of the data. Like I said, we use this on a daily basis. So most of us are familiar with search engines like Google, where you type a few words or some search phrases and then it searches for you and gives you the results that are related to your search. They may not contain the exact words that you've entered, but it will be some variation or something based on relevance. Of course, there's a lot of research and work that has gone into that search algorithm, but the basic idea is still the same. In this case, the data is basically all of the web pages available on the internet. And like I said, the search is not always exact. Something else, when you're searching for products or items on something like Amazon, for example, in this case, the data is all the product information containing product names, titles, summaries, descriptions, specs, categories, all this stuff. It looks for that search terms within all that information and then produces the results again based on the relevance to your search query. So how does a search engine work? If you are curious to know about how all these famous search engines work, or if you're developing an application and you think that it would require some text search functionality, this is how it works. We usually start from the input data, usually a collection of documents or some form of data that contains a lot of text. This text goes through a text pre-processing step, also sometimes referred to as indexing, which is not an exact terminology. We'll say why in a little bit, but we can call this step indexing, but the more formal term would be pre-processing. So this results in some search indexes, and then the search engine is on top of that, which allows the capabilities for a user to submit a search query. The search engine would take that search query, use it to query the indexes, and then return back the results. This is the high-level overview of the whole text search process. Now let's drill a little bit into that text pre-processing step and see what that actually involves. So in this process, first of all, we start with each of the input documents. So we'll take one document. The first step that we do on that document is something called tokenization. Tokenization means, well, first we're trying basically to convert that document, which has just a bunch of unstructured text. We're trying to give it some form of structure, because this structure is what we're going to use to build the indexes and also to help us search later on. So the first step to produce that structure is the tokenization step, which is just as simple as breaking down the text into individual units, or what we call tokens. So if we have a text like this, tokenization would be as simple as just splitting it into separate words. So each of these is going to be a token. So this is the first step of structuring our input data. Now, once we're done with the tokenization, the next step is usually removing stop words. Stop words are any words that are very common and not very useful in search. Things like the, a, an, is, on, for, of, to, all these words. Probably you can find them in pretty much every sentence or every piece of text, and they do not really help you much when you're searching for something. So for that purpose, these are usually removed from the list of tokens that we have. So if we start with this list of tokens from the previous step, we're going to locate all the stop words and then remove them, so we end up with a smaller set of tokens. This helps reduce the index size and also improve the search speed by a lot. Now, once we're done with this step, the next step is what we call stemming. Stemming means basically converting all words to their common form. So things like, different conjugations of the same verb are reduced to a common form. Words that are, singular or plural also would be reduced to a, common form, and so on. This helps when you're trying to look for specific words. Then it can find documents that maybe contain a slightly different form of these words. So in this list of tokens, for example, it can potentially, transform the word jumps into jump. There might be other transformation that happens, but just, this is an example to illustrate the idea. So these steps are done per document. So this is for one document. The same thing happens for each of the other documents in the input collection. And once we're done with that, then we go to the final step, which is building the index. That's why I said indexing is maybe not the right word to describe the whole process, because this is just the final step of the process. But this is where the index is actually built. For text search, the kind of indexes that we usually use is something called inverted indexes. An inverted index is basically a structure that maps terms to the documents that they appear in. Think of it as the index that you can see at the end of a textbook, for example, right? Where you see all the words in the book in alphabetical order, and in front of each word, you're going to see the pages that, this word can be found. So starting with some documents, after we remove the stop words, then we end up with an index like this with all the remaining tokens, and each token has pointers to the pages or the documents that it appears in. So this helps when you're looking for any specific word. Then you can look up this index and figure out, okay, this word exists in these documents, so then you can return those documents. So this is the kind of structure that we eventually produce, and this is what is used in the search. So now the search part, the user submits a query, the search engine will query that index and return the results. Of course, the queries can be, as complex or as simple depending on the functionality provided by the search engine. Some search engines provide capabilities to do, intersection of terms. For example, you want to search for this term and this term, so you only return the documents that contain both. Some search engine give you the capability to say, I want these two terms have to be next to each other, or with maximum 2 words in between, or something like that. So the complexity of the search query depends on the search engine and the functionality that it provides. Now, how does this all relate to databases? This is just, functionality of search engines in general. Databases, as we know them, when they were originally created, they were not really targeted for this kind of queries or this kind of uses, right? Databases were traditionally used for structured queries. Queries when you compare a certain field or column with an exact value, and that's it. That's why it's even called structured query language, because the queries are structured, the data is structured, and so on. So you will look for something like, say where department equals support. So you're looking for this specific field and you're comparing it with this specific value. Not an approximate match. You want the exact match, only the rows that have this exact value, or something like this, where order status in, delivered or canceled. So it has to be one of these exact values. Or you could have where, age is greater than 30. So again, you have an exact value and you want everything that's greater than that exact value. So the queries are usually very structured. Any variation in the data will not satisfy the query. For example, let's say you have a department that has customer support. If I'm looking for support, then this department will not satisfy the query, even though it contains the word support, but our queries are usually exact match. It has to match the whole value. So this would not match. Same thing, if you have an order status that says delivered, but it happens to be, has a space at the end, whoever entered it, entered with a space, again, this will not satisfy this query and will not be returned. So traditionally, the queries have to be matching exact values. Of course, later on, people realize that there is a need for this, non-exact pattern matching. Like I want to look for support, for example, but it doesn't have to be the whole value. I want to find anything that contains the word support, somewhere. So new operations were introduced to handle this kind of queries. Most notably, we have the like operator in SQL, which you can provide a pattern with some wildcards to then allow the system to look for, partial matches, like, a string that may contain somewhere in the string this pattern that I'm giving, and if it finds it, then it can return it. So let's say I have a table that has some recipes, like food recipes in it. Let's just see what the data looks like. So I'm going to say select star from recipes, and let's limit that to 10 rows just to get a sample of the data. So each recipe, we have the title of the recipe, we have a summary, the author of that recipe, as well as the ingredients. Of course, we have a lot more than 10 rows. If I do select count star from that table, we will get 1,000 rows. So it has a decent amount of data. Of course, this is nothing compared to any data that you would see in practice, but it's still not that small. So let's say that we want to look for all the recipes where the ingredients have something that has the word baking in it, like baking soda, baking powder, something like that. So we can do that using the like operator. So I could do something like this: select star from recipes where ingredient like, and I can use the wildcards with baking. So anything that has the word baking in it with anything before it and anything after it should be part of the result. So if I run this query, I will get these two rows. So as you can see in the ingredients field, the first one has baking here, and the other one has baking all the way over here. So this is how the pattern matching using the like operator works. However, usually, when you're searching for something, you don't really specify, like it doesn't have to be in the ingredients. Like maybe there's baking in the summary or in the title, right? So we need to add a little bit more conditions here. So we can say if ingredients has baking, or the title is also like baking, or summary like baking. So we have to basically include all the fields that might potentially have the terms that we're looking for. So let me run this query. Okay, no difference. It's still the same two rows that we have. One thing to note here is that whatever terms you specify, the engine is going to look for them exactly. Like it has to exactly match the word baking. If something has the word baked or bake or something, it's not going to show up. So let's say we also want to look for anything that has bake, not just baking. And let's suppose that we're going to look for that in the summary. So again, we have to add more conditions. So I'm going to say, or summary like bake. So if we run this, now we get one extra result. As you can see here, this one here has baked. So baked, part of it is bake with something after it. So it matches the new pattern that we have. It did not match the old pattern that we had before. Of course, one could say, okay, why do we have to do this? We could just write a pattern that has the letters B, A, K with wildcards before and after. This should match both, which is true. In this particular case, it is true, but in other cases, it might not be true. So again, when you have things like that words can have multiple forms or multiple similar forms, sometimes you have to specify them explicitly. Another thing to take care of is that the matching is also case sensitive. So whatever case we wrote in the patterns, the words or the actual strings that are in the text have to match that explicitly. So if we found baking with uppercase B, for example, it will not match. So let's actually try that. Let's say that the title may have, if I change the pattern for the title here and put an uppercase B, for example, instead of the lowercase b. So let's run this. Okay, now we got 4 rows because we have one extra row here that has baking with an uppercase B. So again, it just shows the limitations of pattern matching using like. It has to be case sensitive. It has to match exactly the pattern that we're putting. So as we've seen in the examples, using the like operation sure helps in finding some patterns, but it also has some limitations. Like it cannot find words that maybe have a slightly different form from the word that I provided. For example, bake versus baking, slightly different, so it will not be able to find it. Also, case sensitivity. It's very sensitive in how you supply the query, and if it doesn't match the case of the data, then it will not be returned, and so on. So there are still some things that you cannot do with like. And if you remember the steps that we mentioned earlier in the pre-processing, many of these steps actually are intended to address these issues. Things like removing stop words, tokenization, stemming, and all that are intended to help with these issues. Another limitation of like is the performance, especially when you're using wildcards in the beginning and at the end of the pattern. In this case, you have to do a full table scan. You cannot use indexes with that. So again, the performance becomes really not that efficient. So due to the limitations of like, some database engines started to add even more functionality to support actual text search, not just this form of pattern matching, but a text search that is actually very close to what we see in search engines like Google and so on. This is something that databases handle differently, so each database has its own syntax for this kind of thing. I will show some examples today using the Postgres syntax, but just keep in mind that if you're using some other system like MongoDB or MySQL and so on, the syntax will be different there. So feel free to refer back to the documentation of whichever system that you're using and see if it supports text search or not and what the syntax looks like. But like I said, today we're going to be showing examples on Postgres. So in Postgres, in order to support text search, the system provides some new functionality, starting with data types. So the first thing is that we have two data types that are used primarily for text search. First data type is something that we call TS vector. TS stands for text search, so text search vector. And this represents a pre-processed input text. So given the input text is usually just a string or unstructured text. So we want to do the pre-processing step that we talked about and produced a structured form of that, which can then be used for text search. That structured form is the type TS vector. The other type is TS query. This is, again, the structured form of the search query that we provide. So whatever search terms that we're looking to provide, it also does some pre-processing on them and produces this TS query, or it needs to produce this TS query before we can actually use that in the search. So in order to do the search, your data has to be in the TS vector form and your query has to be in the TS query form. How to get from strings to these forms? Using some new functions. So there is a function to_TS vector. So it takes a string text and produces a TS vector. So basically this function does all that pre-processing that we talked about. It does the tokenization, the stemming, the removal of stop words, and produces that structured format, which is later used in the search. And on the other side, there is to_TS query, which again does something similar with the query text. It produces a structured format of that. And then once we have those two, we can use this operation, the double add symbol, which basically checks whether the given TS vector, which is data, satisfies a given TS query. So you can use this in the where clause saying, where this TS vector double add TS query, and it will return true if they match, or it will return false if they don't. So this is kind of like the main operations in Postgres. There are some other functions aside from to_TS vector and to_TS query that provide a little bit more advanced capabilities, but we're not going to get into these today. Okay, let's look at those functions, the to_TS vector and to_TS query, starting with the TS vector one. So suppose that we have the summary field again. So if I do select summary from recipes, so this is just going to select all the summary fields. Now, if we want to search into this summary field, then we have to build a TS vector on it. So we do that using the function to_TS vector. Sorry, it doesn't have an underscore here. So basically this returns a TS vector form of whatever we inputted that function. So if I put the summary field here, then let's see what that looks like. So here it just created a TS vector on the fly from the summary field, as you can see here. What kind of information do we have in there? go back to the steps that we mentioned earlier for text searching, or specifically for the pre-processing part of text search. We said that each document, or in this case, each input text, goes through tokenization, removal of stop words, stemming, right? This is exactly what happens here. So the input, which is the summary field, gets tokenized. It gets split into tokens. The tokens, we maintain the position of these tokens within the original string. We remove all the tokens that represent stop words, things like a, to, a, of, in, and such words. So you can see it's not visible in the output. And then the remaining ones are stemmed, meaning that they are kind of like normalized to a common origin or common, form, so that if you have multiple forms of the same word, they will all be converted to that common form. So you can see something like achieve, for example, or achieving, it became this form, like softness became soft. So things are kind of like, reduced to some common form, so that it makes it easier to search afterwards. And we also maintain the position of every word or every token in the original string. So for example, achieve comes from a word that was in the fourth position. So you can see here 1, 2, 3, 4. So this was in the fourth position. Of course, again, all the stop words were removed, but we maintained the original position in the string. And the same thing applies to the other the other rows as well. So this is basically what the function 2tsVector does. Of course, again, if we want to look into other fields, not just the summary fields, let's say we want to be able to search in anything, including the summary, the title, the ingredients, and so on. So we can actually add those in here by concatenating those different fields. So I can do something like this. So summary, concatenate that with a space, and then with the title, and then with another space, and then with the ingredients. And let me actually remove this one so that we can just see the output here. So basically what I'm saying here is that we're concatenating those three fields into one long string and then inputting that into the 2tsVector function. So let's see what the output looks like. This is the output. So of course, now the string is bigger, so there are more tokens. Some tokens may appear more than once, something like bread here, it appeared more than once. Probably it appeared once in the maybe summary and once in the ingredients or something like that. So we still maintain all the positions. And again, the stemming is still happening, the removing the stop words is still happening, and so on. So this is the way to prepare something in order to be able to search into it afterwards. Now, okay, so this is used for the original or the input text, right? For the search query or the search terms that we have, we use a different function, which is 2tsQuery. So let's say if I want to search for the word baking, I have to convert it to a structured form using that function. So I'm going to say 2tsQuery, and then I'm going to give it the search term, which is baking. So if I run this, this will just give us this result, which is bake. So basically what it did is that it tokenized the search query and did the same thing, like stop word removal and stemming and so on. So basically it reduced the word baking into the word bake. You could also use other operations like and or and stuff like that. So if we say and butter, so basically you want to search for both the word baking and the word butter, or that any form of these into some input text. So the query, the structured form of the query will look like this. So basically, again, it did the tokenization and understand that this is an AND operation, and these are the two terms that we're looking for with a conjunction. If we replace this with an OR, then it will look like this. So again, this is just the structured form of the search query that will be used to actually search through the actual data that we have. All right, so now we know how to convert the input data as well as the query to these types, the tsVector and the tsQuery types. So how do we actually do the search? So now we can use the and operation, which basically checks whether a tsVector satisfies a tsQuery or not. So I'm going to say select star from recipes, where I'm going to take this whole thing and I'm going to put this operation here, and then I'm going to say this tsQuery. Actually, let's just search for baking first. So basically what I'm saying is that find me all the rows where the tsVector form of these three fields together matches this query that the thing that I'm trying to search for. So now if we run this, we get these 5 results. So basically anything that contains the word baking or some form of the word baking, this could be baking with a different uppercase, for example. It could be baked. It could be something else. So as long as it matches some form of that, and again, because we have all the three fields in here, it's basically looking into a combination of all those three fields. So this is one way to do that search. It's much easier than what we did using the like operation earlier. We could also add another term. So if we add butter here with an or, so again, anything now that contains some form of baking or some form of butter will appear in the results. So we have the 5 results from before, and we also have things like this one that has the word butter in it. So again, this is how you can do a text search in this case. Let's see the plan of this query, because we always care to see what the plan looks like and how the query is actually executed. So if I do explain analyze on this and I run, so now we can see this is a sequential scan with this filter as expected. This is the same filter that we have in the query. One thing to note is that this TS vector is being computed on the fly, right? Like for every row, we're basically scanning the whole table, the 1,000 rows in the table. For each row, we're going to create the TS vector and then apply this filter comparing the TS vector that we're creating to the TS query. So this is an expensive process. Like, doing this vector on the fly is expensive. As we can see here, the execution time is 17 milliseconds. Of course, it appears to be a small number, but that's because we only have 1,000 rows. If you do this on a large data set that has millions or billions of rows, this is going to take quite a while. So clearly, this is not the most efficient way to do a query like this. If you look back at the steps that we talked about, again, this 2TS vector function, it covers those 3 steps: the tokenization, removing the stop words, and stemming. In the examples that we've seen, we actually performed that at query time. In order to improve the performance, it's actually better to do this as a pre-processing step. So instead of waiting to do that with every query, we can do that, early on and store the results somewhere. And also, build an index on that, like an inverted index, to help speeding up the query. Okay, so the thing that we saw here was that this query was expensive because we were constructing that vector on the fly. But what about if we construct this vector as a pre-processing step, right? So let me do this. Let me alter table recipes. I'm going to add column. I'm going to call it search vector with the type as TS vector. And this column is generated using this formula, which is, pretty much the same formula that we have before to construct the TS vector. And this column is also stored in the table. So what this says basically is that I'm going to add this new computed column. This is the column that gets generated automatically every time I insert a new row or update a row. It's going to compute the value of this function and store the result in that additional column. So let me run this command. Okay, so we just added the new column. If we scroll up and just select from the table again, like we did before, now we can see we have the original columns, and now we have this new column, search vector, that has the TS vector that we have seen already. So this is now stored in the table. This is part of the table. We don't need to construct it on the fly every time we have a query. Now we can just query this column directly, which saves us the cost of recreating it. So now what I can do is that in my query, let's remove this. Instead of applying the condition or recomputing this, I'm just going to say where search vector, the new column that I just created, matches this TS query. So again, I can run this query. This is the results that we have. These are the ones that satisfy this query. And now if we do explain analyze, it's still a sequential scan, but at least the filter is easier. We don't have to actually compute the vector. We just have to compare it with the TS query, right? So that saves a lot of the cost. And we can see here the execution time, instead of the 17 milliseconds that it had before, now it's just 3.6 milliseconds. So it dropped a lot. This by itself is not enough. Like, this is still doing a full table scan, as we can see here. We can change that. We can save this even further by creating an index. We have seen in the steps earlier that the final step was creating the inverted index that tells you which term appears in which documents or which input rows, for example, right? So let me create that index. I'm going to call this index recipe search index, and we're using GIN. GIN is shortcut for generalized inverted index in Postgres. So this is the form of indexes that we use for text search. So and we're building that on the new column, the search vector that we just created. So let's run this. So now the index has been created. Now, if I run that same query from before, Let's do the explain analyze here. Now we're not doing the table scan anymore. We're doing an index scan. So we're doing the index scan with that index condition. It's doing, a couple of different checks afterwards, but basically we're not doing a full table scan. We're using the index. And as we can see here, the execution time has went all the way down to 61 microseconds. So we went from 17 milliseconds to 3 milliseconds, all the way to 61 microseconds with the use of the index. So we can see how we can make this super efficient using indexes. So like I said before, there are other features and capabilities that may be slightly more advanced than what we've shown, but in many applications, what we have here can be sufficient, and you can just use that if this satisfies whatever text search capabilities that your application needs. However, in some cases, these features might not be enough. For example, in terms of performance, if you're dealing with huge amounts of data, this might still become a performance bottleneck. Or if you're dealing with a high level of distributed databases, and you want more real-time operations and so on, or if you want more flexible options in terms of querying and ranking and all that, the features that are found here might not be enough. In those cases, you might have to use some external search frameworks. Things like, you may have heard of Apache Lucene, which is a very famous indexing engine. It is highly customizable. You can, set a lot of different options in there to get, different kinds of indexes and so on. But it's also complex. It adds to the complexity of the system, and you have to maintain basically an external framework. There's also things like Elasticsearch, which is, again, like an external specialized search engine. Provides, functionality for highly distributed, highly scalable data, gives you real-time search capabilities. It also provides you with a JSON-based query language, so it gives you more flexibility in terms of how to query the data or how to search the data. And it can also work on top of Lucene, so you can use the indexes from Lucene with the search capabilities from something like Elasticsearch to get even more advanced and more complex capabilities. But again, I would only recommend going this far if your application actually needs something this complex, because again, it adds to the overhead of maintaining the system. You have separate infrastructure to maintain. You need to synchronize between multiple systems and so on. So it adds complexity to your system. So don't do that just because it's trendy or something. Only do that if you need to. Otherwise, if you don't need that level of capabilities, you can just rely on what's provided by the database directly. So to summarize, today we talked about full text search and how it is critical for many applications and is something that we pretty much rely on in our daily lives. Relational databases, like I've said in the beginning, they were not traditionally intended for this kind of querying, but with the modern capabilities and requirements, they started adding features to support full text search. We have seen some examples on how this is supported on Postgres. But like I said, many other systems also have such capabilities, maybe in slightly different syntax. And finally, if your application requires capabilities beyond what is provided by the databases, you can always use some of the external text search frameworks, things like Lucene or Elasticsearch or many others. I hope this video was useful and shed some light on text search, how it's used, what it's needed for, what are the steps for it. If you have any questions or comments, please let me know, and I will try to get to those as fast as possible. Please like the video if you find it useful. Please subscribe to the channel if you have not done so already, so that you can get the notifications for any new videos that I post. And with that, thank you so much for watching, and I will see you in the next video.